Welcome to this tutorial on CST Studio. Today we are going to be looking at specifically at calculating some figures of merit for accelerator cavities. Now this video is going to be one in a series of videos using CST for particle accelerator physics applications. So let's delve into it. There might be some other videos or there will be some other videos later on going through the steps, but now I'm just going to speed through it, and when the other videos are available I'm going to link to it. Hopefully I can. So for this tutorial we're actually looking at the Eigenmode analysis. We want to get some figures of merit from the Eigenmode analysis, which and the specific figures of merit we are looking at are the arrow vacuum, the peak field ratios, that's your peak electric field, the ratio of the peak electric field to the accelerating field, and also the ratio of the peak magnetic field to the accelerating field. So opening CST, we're welcome with this. If it's not already on new and recent, we just navigate to new and recent, then we go to 3D simulation, then high frequency. Now it opens us to this application frame, and then we see different tabs: home, modeling, simulation, post-processing, and view. We're going to be focusing on post-processing, but then I'll just run a quick model. So the shape I'm actually using for this example is the Tesla cavity, and I should provide a link to the paper that you get the necessary dimensions in the description of the video. So first thing you want to do is to check that your units are in the preferred units. So I prefer working in millimeter and also megahertz, so I change my frequency to millimeter and megahertz, since we do not have temperature is also okay in Kelvin and time in seconds. So that's okay. And then the next thing you want to do is to change your solver type to the Eigenmode solver. You could see different solvers here: time domain solver, frequency solvers, integral equation. But then today we are dealing with Eigenmode solvers because we need some figures of merit with relation to accelerating SRF accelerating, that's superconducting radio frequency, that's SRF, accelerating cavities. So the next is to create a model, and then we go over I can't move this. And the first is to create a model, and for that we go over to modeling. We could use different primitive shapes to actually build a model, but then it's quite easy to, we could perform all operations for a model here, but then it's quite easy to model an accelerating cavity because a macro is already written inbuilt into CST Studio. So we go back home, and then macros, then construct, and then we go to parts, and then we go to superconducting cavity. But before that, let's specify our parameters. So I'm going to be importing parameters, the necessary geometric parameters that we need, but then you can find this in the paper that I'll link in the description. So load parameters from file, and then these are some parameters I have, some accelerating cavity parameters that I already have in my system. So for today we are looking at the Tesla cavity. So this loads in the different parameters. This loads in different parameters, and we see the Eacc, which you would also see in the paper, the BQ, AI, BI, and everything. So this is just the parameter set, and I'll do a tutorial where I show how to actually input these parameters manually. But then for this, because it's like jumping forward in time, because I have like some videos planned, but then this one was just created because it's to fulfill a particular purpose at this time. So maybe I might even do a different one, but who knows. So moving on, I go to macros, and I go to construct, then parts, then superconducting cavity. Then I see the different descriptions. Now you could match the different variables to with different variables here too, the variables we imported. I'm looking at the paper, and already the dimensions already correspond to the Tesla cavity dimensions, which and this is inbuilt in CST Studio, but then we can still change it. So R1 is your iris radius, which is Ri corresponds to Ri. Then we have the length, then we have the equatorial radius, Req. Then we have your iris, the ellipse at the iris, the longitudinal dimension, and then Bi, the vertical, and then Aeq, and then Beq. So okay, and then we have a half cell of accelerating cavity. Now, depending on the coordinate you're working on or the one you prefer, but then you could leave this like this, or then you could rotate it. So it's usually preferred to work in the z-axis such that you consider that the beam is moves along the z-axis. So we're going to be rotating this, and then how do we do that? If component is not already selected, you select your component, then you go to modeling, and then transform. Then you could either translate, rotate, scale, or mirror. So what you want to do is to rotate. Now, want to rotate this about the y-axis, if that's correct. So want to rotate 90 degrees about the y-axis, and then we could preview. So shortcut key to change the view. Now we could change the view with different tools. We could go to we could reset view. We could, and that centers it. Then we could also select view, perspective, and then you see the shortcut. So now you could also press 6. So either you select your view right, or you press 6, and then it gives you the right view. So we could preview, and then you see the preview in the orange highlight, and then you could apply. So that's this, but then we need a full cell, and for this case we're just going to be considering the mid cell. So your Tesla cavity, your standard Tesla cavity has 9 cells, but then with beam pipe, so then we're only going to be considering the mid cells for this tutorial. So one thing we want to do is, another thing I like doing is to center the cavity. So I'm going to be moving this to the central axis. So I'm going to be translating this. Now I could either select copy if I want to copy, but then I do not want to copy it, I just want to move. So I want to translate it by L, which is the length from here to this point. So that's L. So if I should preview, then I see that it moves, and then the mid point is like the mid of the total, because this is just a half cell. So I want to place it so that the cell aligns at the middle of the cell. Yeah, if that makes sense. So I apply, and then another thing I want to do is I want to mirror. So I need to complete the side. So I want to mirror along the z-axis, and then in this case I want to copy, because if I do not click copy, then it just mirrors it, and then I still end up with a half cell. But then if I copy, and then I could also choose unite to make it one body, although that is not necessary. For this case I just copy, and I preview, then I see the complete size form, and then okay, and that's it for the Tesla cavity. Now we see 2 solids because we didn't click unite, but then it doesn't matter for the simulation as long as they are the same material, it's continuous. But then we could also merge this. So if we should go back to modeling, we could also select these 2 solids, and then we could perform a boolean. We could add them, subtract, and all the other things we could do with the shape. So for now we could just leave it, or we could just for demonstration purpose add, so it becomes one solid. So that's it for the Tesla cavity modeling. Then the next thing is to specify a frequency range. Now the Tesla cavity is designed to operate at 1300 megahertz. Now remember, or 1.3 gigahertz. Our unit here is a megahertz, so 1300 megahertz. Now I'm only interested for this tutorial where looking to find, and also the Tesla cavity operates at a fundamental frequency of 1300, which is your TM010 pi mode, and so the fundamental frequency is at 1300 megahertz. Now, since you could have different modes, the spectrum of modes it's very large. We could actually have frequencies up to maybe lots, tons and tons of gigahertz. But then, since we're only interested in the fundamental frequency or the fundamental mode, we put our frequencies around that, because it's actually solving your eigenvalue problem. So we want to just target because the matrix is for the systems. Once you generate your mesh, it's usually large, so we just want to target the frequency so that it reduces the computational time. So I could select just a band around with 1290 because I'm interested in 1300, and I'm just interested in one mode. If you're interested in a spectrum of modes, you could now specify the range to the spectrum of modes. Let's say you are interested in studying the behavior of the modes between 1300 and maybe 1500, then you could specify the range to be maybe 1290 and then 1510 or 1600. So the maximum frequency I want to consider is 1310. So the frequency I'm interested in is 1300, lies between this range. So that's okay, and then you check your background. Now sometimes it's already perfect electric conductor, but as you can see in this case it's normal. So you have to make sure to change it to perfect electric conductor as you get erroneous results. Then your boundary conditions, it's your electric boundary conditions, and I could apply to all. And yeah, you could also change this to magnetic or whatsoever. Then symmetric plates, your longitudinal modes are usually symmetric, and also if you're only interested in longitudinal modes like we're interested in here, you could put your magnetic symmetric planes for your YZ and your XZ planes. But yeah, I'm just going to leave it like this. But then it's not, even if you do not include it, then it can also find transverse, can also solve for transverse eigenmodes. But then in this case, your TM010 mode, which is the mode we're interested in, is a longitudinal mode, so I'm going to leave it to reduce computational time. So click on OK, and then we've set the boundaries, we've set the background, we've set the frequency. Now over to the solver, or before the solver, if you should click on the solver and then you see this pop up and then you solve, you specify your frequency above and you solve, it automatically generates a mesh. But then you could also control your mesh quality or see your mesh before you actually run the analysis from this point. So you click on global properties and then you go to update, and then it updates it. So you see the mesh, it's a bit coarse, so you could actually play around with the values depending on what you want. So I'll leave this at or I could maybe just leave it at 10 so it doesn't take time to compute, since we are not very interested in the we just want to show the how to calculate some values. So maybe yeah, leave it at 10. And okay, now we're ready to solve our system, and then we have your tetrahedral mesh. You could also change it to a hexahedral mesh for some applications. Only hexahedral mesh is work, but then for Eigenmode solved by tetrahedral mesh is okay. You could also change to preview, which is actually faster, solves faster, but then at this point I do not actually know what you lose in the preview. Yeah, but yeah, it actually solves faster. That's all I know for this point. So we want frequencies. We want to calculate for frequencies above 1290, and then we do not want to refine tetrahedral mesh. Consider losses in post-processing only. You could leave that checked. It doesn't really apply to this. So we could choose to calculate for 1 mode, 2 modes, 3 modes, 5 mode, 10 modes, whatsoever. But then we're only interested in 1 mode. So we click on start, and then okay, so it solves the eigenvalue problem with the boundary conditions is specified, and then it's done. So we see that this actually gives us, when you go to your results, 2D, 3D results, you could see your electric field profile, you could see your magnetic field profile. Now you could see that this is, I just pressed 3, which gives me the front view. You could see that this is your magnetic and field profile. Then you could look at the fields on the plane. So you could look at the fields on the plane by clicking this, and then this 0. You could then move, and then you look at the electric field, the magnetic field also. So that's that. Now back to the now to the main point of this tutorial is evaluating some figures of merit. So I mentioned earlier that what I'm interested in is calculating the R over Q, the peak field ratios, and the peak field ratios, but then I might show some other things. So going to the result templates, we have okay, so you've done with the simulation, you've seen your results, your 2D and 3D Eigenmode results. So you have your 1D results also, which is the mode frequency. So since we only calculated for one mode, you could only see one mode, 1300.84. I think maybe if you refine the mesh, you would have more accurate values. So this is what we have, and then we move over to the post-processing tab, and then we see result templates. So this is where we do all our post-processing, and then we have 2D, 3D field results, which are your electric field and your magnetic field. Now you could play around with so many settings, or maybe you could integrate the field along a path and some other things. But yeah, let's go. First of all, we go to 2D, 3D field results. Then we could now look at 3D Eigenmode results. Scroll to 3D Eigenmode result, and then you get a list of quantities you could calculate for. Our frequency is already known, but then you might need to calculate your frequency to mix it with, we could mix your frequency with some other results, so you might need to calculate it also. So I could just click all or just mode 1, but then since we have just one mode, I could just calculate the frequency, and then what this does is you evaluate it, and then it calculates the frequency, then creates a frequency, a result in your 1D. You can see it creates a result in your 1D results. Now you could duplicate this, and then settings, and then you go to we're interested in also okay, one thing to mention is that the energy in your CST, your Eigenmode simulation, is normalized to 1 joules. So if you calculate it, you could also confirm by calculating the total energy, and then you evaluate it, and then this takes a bit of time. Okay, and then you see that it's 0.99, so approximately 1 joule. So it's always normalized to 1 joule. Then you could also duplicate, or you could go back to 3D Eigenmode results, and then what you're interested in is your R over Q, which is a very important figure of merit in accelerator cavities. So now we want to calculate R over Q for the entire length of the cavity. Now while this pop-up is available, we could also, but we can't for this, but then some pop-ups we could actually still play around with. We could actually still navigate to some places in the software. So we want to calculate the R over Q along the Z, and we want to calculate it in the mid-axis, which is your x is equal to 0, your y is equal to 0. Then for the maximum range, of the cavity, then particle velocity beta is equal to 1, which is just your v over c, which is equal to 1. That's velocity of the particle with relative to that of the speed of light. So ideally, or I think it should be made that this should be available, but then it says only available. That's to see the point you are, to see the line you are calculating your R over Q. Sorry, the R over Q for, but then it's not yet. It's not like that. You have to evaluate it first. So click on R over Q. You evaluate, and then you can now go to see the point. So it's correct. We're evaluating the R over Q along this line from beginning to end. Okay, we can't. We just see the line, and then that's it. So R over Q is 113.32, and then you could also try to confirm this from the paper that will be linked below to see how they differ, by how much they differ. So, and then one other thing is calculating the peak field ratios. Now, to calculate the peak, now this sometimes this actually changes the default display to default when you view the draw point. It changes the display to I think wireframe. So you could go to view, and then you change the display back from wireframe, and then this is not supposed to be, the draw points are supposed to disappear, but I don't know why it doesn't. It just stays there, but then that's not important. So how to evaluate, because what we're interested in is the surface, the peak surface field, the ratio of the peak surface field to the accelerating field. Now we're going to calculate the accelerating field later, but then since we want to evaluate the peak, which is the maximum electric field value on the surface, we have to create a surface. Now we could create a surface, we could create a line, we could create points, we could create whatever we want. And then how do we do that? We go to our modeling, and then we could pick, right? Or we could even draw our own personalized curves. But then for this case, we want to pick faces or face chain. So since we want to calculate, so it picks the face chain, so it picks all the faces, we could also click on, now we should go to picks, we could clear picks. So we could also clear picks, but then the shortcut to pick face is F. So I press F, and then I could pick individual faces, F again. Then to clear picks, the shortcut is D. So I press F, and I pick the faces I want to evaluate on. And then I go over to the left, and then I right click, create faces from pick faces. Yes. So I could name the face whatsoever I want, but in this case I'll just leave it as face 1, and then no offset. So okay. Now we've created our face. Now we go back to our post-processing, result templates, 2D, 3D field result. Remember, we want to get the peak field, so it's still 2D, 3D field results. So you see your field results we're evaluating the peak field from. Now you go to evaluate field on curve or evaluate field on face. So now we want to evaluate on the face, which is the surface. We want to get the maximum surface field. So go to evaluate on face. Now which field results do we need? We need the H. Now you see you also have your energy density, electric and magnetic. So we need the E, sorry, not the H. Okay, we need the E and the H. So for the mode 1, if we calculated for more modes, we'll see different modes here. So okay, and then we need the absolute component and then the magnitude. And then we tick evaluate on surface. Then what do we need? Do we need the integral of the electric field over the entire surface, or the mean value, or the maximum? We could calculate for all of them here. We could also get x coordinate at maximum. We could locate we could get the x and y coordinate of the maximum value of the peak field. But then what we're interested in this case is the maximum value. So okay, and then we could rename this just for, so we could rename this to Eacc, and then we evaluate. So we have our Eacc, and then we could go to our 0D results and then see it here. So these are peak field value, but then it doesn't really make doesn't when I say it doesn't make sense. It's okay, but then your field is, you also have to have in mind that your energy is normalized to 1 joule. So this doesn't mean that this would be the peak field that you would have in application. It's just when you normalize your energy to 1 joule, this is the peak field you would have. Then we could duplicate and then go to settings. Now instead of your E, we go to H, and then still the same settings. Okay, then we could rename this to H. So then we evaluate. So that's the H peak, and then in literature we have E peak over E acceleration and B peak, not H peak. Now what's the relationship between E peak and H peak? It's your B peak is equal to mu H peak. So that's your mu naught H peak. Now we want to, in this case, we want to actually evaluate a different result, which is we want to multiply this result, this your field result, by a value. And how do we do that? We go to 1D, general 1D, one dimensional, and then we go to mix template results. So we want to, now the variables are not giving um, unique names. Would I say unique names? Or the variables are giving unique names, so we only can use variables A, B, C, D to F. So we can't write 1 multiplied by H peak here. That would be wrong. But then instead we assign H peak to A, and that's this. And then we want to multiply A by mu naught. And mu naught is 4 pi epsilon raised to 4 pi E minus 7. But then it's also coded into your CST Studio as mu naught. This is a 0, not an O. So when we click OK, we can evaluate this all runs. And then also keep an eye on this, your messages, so you see if there's any error. So this is our B peak, so we could rename this to B peak. And yes, so that's it. So we've gotten our E peak and our B peak. Now the next thing to find out is V acceleration. So our V acceleration is your E acceleration, which is your accelerating field. Now accelerating field is the accelerating voltage divided the accelerating voltage along the axis, the beam traverses, divided by the total, the length, the forgotten what they call it, but it's length, it's your length. So now we want to get accelerating voltage. Accelerating voltage is gotten from the field, which is we go back to our 2D, 3D field result, and then we go to 3D Eigenmode result, and then we see your accelerating voltage, which is this. Now we want to evaluate your voltage along the center and pointing towards the z-axis. So the same points we found out for your R over Q. Your R over Q is also related to your accelerating voltage. So we have your beta is equal to 1 all modes, or 1 mode 1, and then okay. So we could rename this to your VACC, which is just your V acceleration. So we could evaluate this, and then we want to use V acceleration to calculate for A acceleration, which is going to be dividing it by the length of the cavity. So we go over to, as before, general 1D, then mix template results, and then we want to V acceleration, so we want to do A multiplied, no, not multiplied, divided by, now take note that our dimension is in millimeters. Take note of the dimensions. Our dimension is in millimeters, so we need the length, but then your L is the half cell length, so we multiply by 2, which gives us the total length. Then this is in millimeters, and then we multiply by 1e2 minus 3 to convert to meters. So that gives us the length of the cell, of the cavity cell, that's the mid cell we calculated. So V divided by this length, and then we would have so I'll change this to Eacc, and then we evaluate it all runs, and then we have a value, but then these values on their own do not make sense now. um, but then the ratios of this value is actually what we're interested in. So we want to mix Epic and Eacc, then Bpic and Eacc. So still general 1D result, we go over to mix template results, and then we need Epic and E acceleration, so it's going to be A divided by B, and we could name this Epic Eacc, and then we evaluate this, yes, and then we duplicate. We could do the same thing for the Bpic over Eacc, but then we just duplicate to save time, and then we change this to your Bpic, and that's okay, and we just change the name, housekeeping, and evaluate all runs. So, and that rounds it up. I think that's all for this video. R over Q, I mean, from this you could see that you could actually get so many other parameters. You could actually from your 3D eigenvalue results, you could actually evaluate on curve or on an arbitrary coordinate. Let's say we wanted to see the field profile along the center line, we could evaluate field on arbitrary coordinates, and then we could specify the coordinates. So for example, this is beyond this video, but then we could get the field value of E, the distribution, and then we look at on a 1D line on an area, but then let's look at a 1D line Cartesian direction Z. So we want to get the field profile along the center. Now we change this to 0 and 0, so that's the center, and then from Z min to Z max, and then we, is there any other setting? No, we could just okay, and then we evaluate this, so we see the field profile. So many other things we could do, but then let's look at the peak field ratios. So we go to our results. We have our 1D and our 0D results. Then now let's look at your Epic over Eacc. The value is we could go to maximum 2.04, and then your Bpic over the acceleration is 4.46. Now in the paper that will be linked in the description, you could also see these values that for the Tesla cavity, your Epic over Eacc is 2.0 and your Bpic over Eacc is 4.5. Or is it? I think no, it's 4.2, not 4.5, it's 4.2. So for this, we use a really coarse mesh, so I wasn't expecting the result to be exactly on point. But then if you should refine your mesh and run the analysis again, or if you should, in the analysis setting, you should select and refine tetrahedral mesh, then your answer would be more accurate. So I think that's it for this video, and hopefully I get around to making videos for the modeling and some other things, and don't have to rush over them. So yeah.